Hey, welcome back to Fat Mama Physics. In this video, we are going to do a conservation of energy problem that is in an IB exam. Specifically, this is the, this question is from a standard level paper 2 question from 2018 of May in time zone 1. So if you want to refer back to that question, I took only bits and pieces of that question just for conservation of energy. So let's try this out. Here we have an elastic climbing rope is tested by fixing one end of the rope to the top of a crane. So there's that block right there. The other end of the rope is connected to a block which is initially in position A. The block is released from rest, which we know the initial energy of speed here is 0. The mass of the rope is negligible, so we don't have to consider that in our energy equation. The unextended length of the rope is 60 meters. From position A to B, from position A to B, the block falls freely, and that just means it's not going to stretch the rope or anything, it's just falling, essentially. At position C, the speed of the block reaches 0. So here we have the speed being 0. I'm just going to write that down. The mass of the block is 80 kilograms, and starting with A, describe the energy changes that take place as the block passes through points A, B, and then C. So starting at A, we have pretty much we have no kinetic energy. Okay, we know we don't have any elastic potential energy from this rope over here because it's not being stretched or anything. And we also know that because this block is falling freely without doing anything to that climbing rope, is not being stretched. So A, we only have gravitational potential energy, which I'm going to label as EPG, and then I'm going to put here max. Okay. When it goes to point B, some of that gravitational potential energy is going to get converted into kinetic energy, but we still will have some EP left, some gravitational potential energy left relative to, I'm going to assume the bottom being C over here. And at this point, there is still no elastic potential energy, since the block is still falling freely until point B. But after point B, this is where, imagine this block is now stretching this climbing rope. So then at the very bottom, we know that there is no speed, so there's no kinetic energy. And at the very bottom, relative to the very bottom, say let's call that EP is 0 at the bottom, we have no gravitational potential energy, and all we have is the elastic potential energy from the rope. Okay, so I'm actually going to write, since it's a rope or elastic, we're talking about elastic potential energy, I'm going to write EPE for that sake, or I mean, really doesn't matter what symbol you use, as long as you're being consistent. So I'm going to write that down as a sentence for A. Okay, so it's a little bit lengthy, but I try to be as concise as I can. The block starts off with all of its energy in the gravitational potential form at A, in which some of it gets converted to kinetic energy when it reaches point B. And yes, there is some gravitational potential energy left relative to point C. And then going to point C, all this mechanical energy gets converted into elastic potential energy in the climbing rope, and in which there will be no kinetic energy left, and also no gravitational potential energy left relative to point C, if we assume that to be 0 gravitational potential energy. Okay, so now for B, we have at point B, the rope starts to extend. Oh, well, I went ahead of myself there. Calculate the speed of the block at point B. Okay, so we know at point B, that's where that gravitational, at that point, we're going to start getting elastic potential energy. But before that, we know that all of the gravitational potential energy gets converted to kinetic from A to B, okay? So let's say we only care about position B. So I'm going to label position B as my reference point for my gravitational potential energy. I'm going to say here the gravitational potential energy is 0. I can use my energy equation if I want, just to show you how I would use it. Okay, and the initial height we know is 60. There is no speed to start off with, so this goes away, this becomes 0. And relative to point B, we're going to call that potential energy equals 0 joules. So at that point, the final height is 0 relative to B, so we have no gravitational potential energy there. And we are asked to calculate the speed at point B, so that's our final velocity there. So let's simplify this equation. Here we have the masses canceling out nicely. And we're going to solve for VF, so I'm going to multiply both sides by 2. We're going to get 2ghi equals to final velocity squared, so then don't forget to take the square root. We are left with the final velocity equal to the square root of 2 times gravity, 9.81 meters per second squared, and the height is 60 meters. Putting this into our calculator, we get 34.3 meters per second, which we are going to round to 3 sig fig, so that's going to be there, 34.3. Okay, so then last but not least, we have question C, which is the length reached by the rope at C is 77.4 meters. So this is 77.4 meters in total. Suggest how energy considerations could be used to determine the elastic constant of the rope. Okay, so a couple of things here. First of all, the elastic constant of the rope they are referring to is talking about the spring constant K. The other thing you want to read carefully is the command term here. It's called is suggest. Notice it's not calculate. It doesn't want you to calculate the elastic constant of the rope. It just wants you to describe how you would solve this problem instead. However, what I can do on this side of the page is I'm going to, I can show you how you might be able to calculate this. I'm actually going to go ahead and calculate the spring constant for you, just so I can give you I can show you another example. Okay, so let's do what the question is asking first. So you know the length of the rope reached at C is 77.4 meters, in which the rope was loose until it reaches point B. Okay, and it says here at B, at position B, the rope starts to extend. Okay, so when it goes from 60 meters to 77.4 meters, so that means it's the stretching that is being done is the difference between 77.4 meters and 60 meters. So then you do have the amount of, so you know the stretch in the spring here, which means if you have the elastic potential energy, and if you know how much the rope is extending for, then you can calculate K. So let's write that down. Okay, and then now we need the elastic potential energy at point C. And to do that, we need to use conservation of energy. So here I drew a flow chart just to do question A over here. So to find the elastic potential energy, you either need to know the full gravitational potential energy to begin with at point A, or you can know, if you know the kinetic energy and the gravitational potential energy at B, you can also use that to find the elastic potential energy at C. So either or works. So we can write that down. Okay, so then that's how you would get the elastic potential energy, by either knowing what energies you started off at A or at B, and using that elastic potential energy with the extension of the rope to find your elastic constant. In fact, we can do do the calculations right now. So if you just had to answer this question, that's all you need to do, is to suggest a solution. You don't need to go and calculate it, okay? But I will calculate it here as a separate question, let's say for our sake, okay? Okay, so this is what we begin with, and so I'm going to solve for the elastic constant, or our spring constant here. No, given that we know x and EPE. So first I'm going to multiply both sides by 2 to get rid of the half, and divide both sides by x squared to get rid of the x squared. I am left with 2 EPE divided by x squared is equal to my spring constant, okay? So now I just need the elastic potential energy. And I'm going to use point A as my other reference point. So at point A, I have gravitational potential energy relative to point C. Because if I'm going to convert all of this EP, gravitational potential energy, into elastic potential energy. So that's going to be equal to mass times gravity times this height that I have at A, and that's going to be a total of 77.4 meters, not 60 meters, because even between B and C, more gravitational potential energy is being converted into elastic potential energy. So let's calculate this. I get the mass of the block is 80 kilograms times 9.81 times the height, which is 77.4 meters. So then I would get 60743. Okay, and now I can use this energy, because all of this will be converted into elastic potential energy. I can use it in this equation to find my elastic constant. Using x as the 17.4 meters, don't forget to square it, we get 401. And 3 sig figs, that's 401 Newton per meters. Okay. All right, so here we have that problem. Just be careful of the command terms. Don't do extra work, or don't do work that you're not going to get credit for on an IB exam. Hopefully this explains a few things to you and also gives you a kind of like a bungee jump question. So thank you for watching. Hopefully you can use this problem, the skills you developed in this problem, to apply to your practices. Good luck. And Fan Mama Physics signing out.